And in fact, this is the this was the dependence or the conflict graph that we constructed last time. So the conflict graph is A conflicts with all of them, B, C, D, and E. And what's the other conflict?
D.
Yeah, B and D. Okay. So again, just to refresh your memory, here what we are trying to do is global register allocation. What global register allocation means is that we are trying to allocate registers, to allocate physical registers to virtual registers that are located in different basic blocks. So in global register allocation, we are looking at multiple basic blocks at the same time. In this example, we are looking at 4 basic blocks. While in local register allocation, we look only at 1 basic block at a time. Now, let me ask, what's the advantage what's the advantage and the disadvantage of local register allocation? So local register allocation has an advantage and has a disadvantage. So that should have been, yeah, obvious. Yeah.
Well, local register allocation is generally simpler to implement. It's easier to allocate physical registers.
Mm-hmm.
The disadvantage is that any values that need to be carried over to another block need to be stored.
Yeah, exactly. So this is exactly what the advantages and disadvantages of local register allocation. Local register allocation is much simpler. It's one pass. It's a linear pass through the code, as we have seen in previous lectures. So it's simple to implement. So in terms of compile time, it's good. So it doesn't require a lot of compile time. By the way, in the context in compilers, we talk about compile time and we talk about performance. So when we say performance in compilers, we mean the speed of the generated code, not the speed of the compiler itself. Okay. So you compile a program. So when you are compiling a program, the speed of the compilation process is what we refer to as the compile time or the compile speed. While the speed of the program that gets generated out of the process, out of the compilation process, this is what we refer to as the performance. Okay. So in local register allocation gives good compile time, but it gives, in general, it gives poor performance because the generated code will have excessive loads and stores, and these excessive loads and stores come from having to load everything before you use it in a basic block. Everything gets loaded before it's used in the first time in a basic block, and everything that is defined in a basic block gets stored. So you do not carry values across basic blocks. Basically, anything that is happening across basic blocks is stored where? Anything across basic blocks
Stored in memory.
is stored in memory as opposed to register. So anything that is live across basic blocks, you're not storing it in registers. You are storing it in memory. So you are loading it before the first use in a block, and you are storing after the last definition in a block. Okay, so now this is our global register allocation. Now it's a global analysis. We analyzed the live ranges, and in this case, there is one live range for every variable or every virtual register in this case. By the way, generally speaking, a virtual register will not necessarily have a single live range. So to give an example, if we add here, and I will just add this temporarily, and then I will remove it. So if we add something like define A and use A. So this little definition of A and use of A, this is going to create a different live range. It's not the same live range because this live range, this definition of A gets used. It gets used here, and it gets used here. So this live range of A, this is a definition, and these are the uses of this definition. Now the question is, does this definition of A reach this point? It does not. So this definition, this particular definition of A, does not reach this point because it will get overwritten or killed by this definition of A. So this definition of A, a new definition, a different definition of A, is going to kill this definition. So the definition that reaches this use of A is going to be this definition, not this. Okay. Now what does this mean? So this means that if we were to solve this problem, with this addition in red, we will have two live ranges that are associated with this virtual registers. We have a live range, the big live range that we already have here, and we'll have another A2 live range, which in this case does not conflict with anything. This does not, in this example, does not conflict with anything. But the point is, this is a different live range. So a live range will have all the definition. It will have, for every use, you have to have all the definitions that reach that use. And for every definition, you have to have all the uses that are reached by that definition. So let me write this down. So in a live range, okay, we must have, for every definition, all the uses that are reached by that. For every definition, all the uses that are reached by that definition must be in the same range in forming live ranges. And for every use, all the definitions that reach that use must be in the same range or live range. Okay, so for example, this is a definition. The uses that are reached by this definition are only this, so they are in this live range. This is a use. All the definitions that reach this use, in this case, is only this, so this will form a live range. For this live range, for this definition, all the uses that are reached by this definition, this use and this use, must be in the same live range. And again, for this use, you have to have all the definitions that reach it. Yes?
If you did not have the last two lines and you put a definition on the second block, right above the def B.
Okay, if I don't have these in red?
And you put the define A on the left, the second row, the left block.
Here?
Go up.
Oh.
That block, define A.
Mm-hmm. Okay, so you want define A here?
Yeah, it doesn't matter.
Okay.
Which use A will that be on the last block?
Okay. So in this case, it's an excellent question. So if I have this definition of A, and A is not defined here, Well, this is an excellent question. So now this use, in fact, both of these definitions may reach this use. So this definition can reach this use of A, and this definition of A can reach this use of A. So there are two reaching definitions, and both definitions should be in the same live range. So every definition that reaches this use should be in the same live range. So for this use, you must have this definition and this definition. So there may be multiple definitions that reach a use.
For my clarification, would you have two use A's on the last block?
Why to use? No.
I didn't understand your
No.
answer.
It's a single use. So the live range will have to include both definitions. So the live range will have this definition, and this use. So they will all belong, and this use. So the live range of A will include this, 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 this. So these four definitions and uses, they will all belong to the same live range. All four of them, because they are all related. Okay? So in fact, that was an excellent question. Okay, so now let's remove this and get back to our example. Okay, now the point is we have this conflict graph, and we have only two physical registers. Two physical registers. So because we have a clique of size 3, as we said last time, we have a clique of size 3. These all conflict with each other. We can't do it with two physical registers. We must spill. The question is what to spill. And last time we didn't get the chance to do it in detail. In detail, we would like to compute a spill cost for each node. And that spill cost is going to be for each node. It's going to be for each definition. You multiply it by the cost of the instruction that you will have to insert. Now, if you spill A, for example, you'll have to insert a store. Where do you insert stores when you spill?
Right after the define.
Yeah, exactly. You insert a store after a define. Insert a store after every define. And a load, where do you insert a load?
Before each use.
Before each use, yeah. And a load before each use. So now this means that the spill cost is going to be, I'm going to have to count how many loads and stores I will have to insert. But it's not just the sum of loads and stores. It has to be a weighted sum that takes into account the frequency of execution of each basic block. And let's assume that we are given these frequencies of execution. This has a frequency of 1. This has a frequency of a half virtually because we are splitting here. And this has a frequency of execution of 10. So we are assuming that this is inside some loop that is not shown here. So we're not showing this loop, but we are assuming, to simplify things, that this is going to be inside a loop, and the loop will get executed 10 times. And like I said last time, in general, the compiler doesn't know exactly how many times each loop will get executed. It may come up with some estimates, static estimates, and sometimes it may base these counts on profiling information. So there is profile directed or profile guided compilation, where the compiler will generate an initial value, some starting value of the code. Oh, I'm sorry. I apologize. I forgot. Yeah, so the compiler will generate an initial version of the code, and it will do it will run it. You will run it, the user will run it, and it will generate profiling information. And based on that profiling information, it will recompile again using the profiling information. Okay, so now in this case, the spill cost, let's calculate. Let's assume some weights for the loads and stores. So let's assume that cost of a load is 2 and cost of a store is 1. Let's assume that the load is more expensive than the store. Why is that? Because the load, with the load you will have to wait for that value to get loaded into a register and become available. While for a store you do not have to wait. You just write it to memory. So the spill cost for A is going to equal this. We will have to insert a store. So it's going to be 1 cost of a store times there is only one definition of A times 1. So we multiply for each block number of definitions. Let's write it here. Okay. Cost for defs, number of defs multiplied by cost of store multiplied by execution frequency of the basic block. Cost for load, or for use, is going to be number of uses times cost of load times execution frequency. So for A, we'll have 1 times 1 in this basic block. Or in fact, it's 1 because there is one definition. So it's one definition. The cost is 1, and the execution frequency is 1. In this basic block, we don't have any A. In this basic block, we have a use of A. So we will have 1 use multiplied by the cost of a load, which is 2, by the execution frequency, which is 0.5. Here, we have 1 use of A. So we will have 1 times the cost of a load or a store? Load, which is 2. And what's the frequency? 10. So what will be the spill cost for A? So this is going to be 1 plus 1 plus 20. So that's going to be 22. So we label this with 22. Spill cost for B. What's the spill cost for B? The spill cost for B, we have B in this basic block. So we have a definition and a use. So for the definition, there is only one definition. And the cost of a store is 1. And the execution frequency is 0.5. And there is a use with the cost of a load is 2, and the execution frequency, this is multiplied by 0.5. This is for B, right? So for B, we have 1 times 0.5. This is 0.5. 0.5 plus 0.5 times 1. So this is going to be, this is 0.5 and this is 1. So it's 1.5. Spill cost for C, it's going to be same as B, right? So there is a definition and there is a use. So it's going to be 1.5 because it's the same as B. Cost for spill cost for D. There is a definition of D here, so it's 1 times 1
D.
times D. So yeah, sorry, I'm looking at A. So for D, yeah, there is a definition here. So 1 times 1 times 0.5, and there is a use of D here. So it's 1 times 2 times 0.5.
I believe in the prior example.
Yeah, that should be a def.
Yeah, that's a definition, not a use.
Yeah, because there's no defined prior to it in that code.
Okay, so this, yeah, I guess you are right. So this is a definition. Thank you for catching this. So this is a definition. So this means that this is also a 1. And the use of D here, we have 1 times what? 2 times 10. So this will give us 0.5 and 0.5 is 1. It's going to be 21. And spill cost of E, and E is again local.
It's 3.
Yeah, so it's going to be 1 times 1 times 1 plus 1 times 2 times 1, and that's going to be 3. So you label each one with its spill cost. So this is 22. This is for B, it's 1.5. For C, it's 1.5. For D, it's 21. For E, it's 3.
Now I have a question here about this. For D, since the definitions appear in parallel blocks of code, shouldn't that only be counted once instead of twice?
Well, it's once instead of twice, but you never know, right? It's the question. Well, the answer is no, because both are possible, and by setting the weight of this to a half and the weight of this to a half, we're saying that it's 50% chance we will be executing this, 50% chance we will be executing this. So they are not in parallel. There are two possibilities. So we will be either here or here. This is not parallel execution. So it's either this or that. So it's probabilistic. And this is the point in factoring the execution weight or the execution probability into this calculation.
Okay, yeah.
Okay, so this is the point in doing the half here. Okay? All right. So now we need to select something for spilling. So first of all, the one thing that we can do to simplify things is to identify the easy nodes, the nodes that are not problematic, that can be colored easily. And those are the nodes whose the number of for which the number of conflicts is less than the number of physical registers. So for C and E, the number of conflicts for C is 1, the number of conflicts for E is 1, and 1 is less than the number of physical registers. What does it mean? It means that you can always color them easily. You will never fail to color them, because C only has to have a different color than A, right? So no matter how you color the rest, you're going to find a color for C, and you're going to find a color for E. So nodes that have nodes with degree less than number of physical registers can be colored easily without a problem. So you just eliminate them. Just, I leave them. I can leave the coloring of these until the end, until I figure out what the color of A is, and I will just give C a different color than A, and then I will just give E a different color than A. So I only am left with the 3 ones that have conflict. So which one has the lowest cost?
B.
B. So I try to spill B. So what I do is, after the definition of B, I put a store B. And before the use of B, I put a load. So this is what's spilling B. So I spill B. Then after spilling B, I check if this has resolved any conflicts and if this has made things any better. So now, in fact, this becomes B1 and this is B2. Then load B2. Sorry, this is B1. And this is load B2 and use B2. Now, I redraw the graph. Redrawing the graph now, B1 will B1 conflict with A? Will B1 conflict with A?
Yes.
Yeah. So A is live through the entire basic block. So it's going to be, A is going to conflict with B1, and it's going to conflict with B2 as well. Because A is live throughout the entire block. Now, how about D? So D conflicts with B1 or B2?
B2.
Yeah, it conflicts with B2 because D starts here after B1 ends. So D is going to conflict with B2, but it does not conflict with B1. Why? Because the live range for B1 now, with the spilling makes the live ranges very tiny. So now this spilling introduces tiny live ranges. So now B1 has this live range. It gets stored here, and that's it. So this does not conflict with D, but what conflicts with D is B2. B2 conflicts with D. Does everyone see this?
Yeah. I have a question here.
Yeah.
So if we spill D.
We haven't spilled D yet.
Yeah, but I'm just saying, if we spill D to allow the use of B2 and then load it again and keep it in a register, wouldn't that work?
It would, but we haven't gotten there yet.
Okay.
So the algorithm will look for the cheapest spill first. So we're describing an algorithm, and this algorithm doesn't know beforehand, which is going to be the best spill or the spill that will reduce conflicts, which spill will reduce conflicts and which will not. So the algorithm wouldn't know if spilling a certain variable or spilling a certain virtual register is going to reduce conflicts or not until it actually spills, and then it rebuilds the conflict graph, and it sees if now we have less conflicts or not. So we don't know beforehand. That's going to be what we will conclude at the end. But right now, we are having these options, and we should be cheap. We should be trying to spill the cheapest first and see if that resolves the problem. We are spilling the cheapest, but it looks like even if we spill the cheapest, we still have this clique of size 3. So we still have 3 conflicting with each other. So this spilling, we added these loads and stores, and it didn't do us any good.
Yeah.
Okay. All right. So so now spilling B did not help. So we will go to the next cheapest. The next cheapest is going to be D, right? So D is 21, and this is 22. So we will go to D. We will consider spilling D. Now, by spilling D, now things are getting messy here. Spilling D, after this define, we put a store D. Okay, and after this we put store D. And what else do we need to insert?
Load.
Yeah, load. Load D. Yeah, so in fact these are going to be different Ds. So now we are storing this D. So this is storing D1. And here when we are loading D2 and store using D2. Now when we look at the conflict graph, does A conflict with D1? Yeah, it still conflicts with D1 because remember that A is live throughout this entire block. It conflicts with anything here. Does A conflict with D2?
No.
No, it doesn't conflict with D2. So this is the last use of A. So here we have D1 and D2 now. Sorry, this should have been a D, by the way. But yeah, so now A conflicts with D1, but A does not conflict with D2. In fact, this D2 here, does it conflict with anything?
No.
It doesn't conflict with anything because we are defining it here. This is a clean definition that we are bringing from memory, and this is a use. So, and it's not conflicting with anything. So D2 is not going to conflict with anything. It's going to introduce, this separate node in the graph. Now, D1 conflicts with A. Now, what's the relation between D1? So this is D1 and B1 and B2. Does D1 conflict with any of B1 or B2? So B1, this is the live range of D1. We're defining it, then we're storing it. That's it. This is the live range. For D1, this is the live range. And for B2, this is the live range. Load and use. So in fact, now with this spilling, this is a tiny range here for B1. This is a tiny range for D1. This is a tiny range for B2, and they do not conflict with each other. Okay. Does everyone see why they do not conflict? Does anyone have a doubt about this? So we're defining B and we're storing it, and this is the last use. We're loading a clean here, a clean copy of B. So we're starting a new live range. So this is a clean version of B. And D, by spilling D, this is the definition and this is the use, so this does not conflict. So you will have, with these spills, like 3 live ranges. Okay. By spilling, you are making live ranges smaller, and you are reducing the number of conflicts. Yeah?
What do you mean by clean again? Sorry.
Clean, you are bringing this from memory. So by loading B, you are bringing a clean copy of B from memory, which means that has nothing to do with this B.
What other types of copies are there if it's not clean?
Well, it gets modified. So if it gets modified, it's no longer clean. So here, what I mean by clean is that this use, we are bringing a fresh copy from memory for this use. So this is a live range by itself because this is a definition. The load is a definition of B, and the use uses B. So remember that a load defines a register, and the store uses a register. So a load defines a register, and a store uses a register. Okay? So right now we have this graph. Now we no longer have 3 nodes conflicting with each other, which means that we can go ahead and color this, and you can just color A, for example, with P1, and these can be colored with P2, 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 and this can be colored. You can choose any color for this, P1 or P2, because it does not conflict with anything. And here for C and E, what should we do with C and E?
P2.
P2, because they conflict with A. So this is P2. This is P2. So the idea is you compute the conflicts, then you spill the cheapest register, and then you check the conflicts. If that makes things better, it makes the graph colorable, then you color. If it doesn't make the graph colorable, you spill the next cheapest live range, and you keep doing this until you eventually you have a colorable graph. Yeah. And in fact, sometimes it's the graph is not the problem is not easy if you don't have enough physical registers. For example, at some point I was fixing a bug in a register allocator where it was not converging. So you keep spilling forever, and it's not converging. You are not getting a colorable graph because you are not having enough physical registers, and that was a bug in the implementation that was causing the number of physical registers to be too small to make the problem solvable. Okay. So any questions on this? Yeah.
So you had to spill both B and D.
Yeah.
To get it to work?
Yeah. So you cannot undo the spilling of B. Yeah. We spilled B. Yeah. So this is an algorithm that spills B, and then it goes with this. Now it has modified the code. Then it spills D. So we committed the spill of B.
Oh, okay.
That's a good question. Okay. Other questions? Any other questions? Yes.
If the code continued on, if there wasn't any register conflictions, would it continue to load and store D, since it defined it?
Yeah, so if we have something else below this point?
If it used D again, would it continue to store and load?
Yeah, so for example, if we had another use of A here, so if we had a use of A, then A would conflict with D. But you are making, the problem. You are making the problem harder. Okay. But if we had a use of A, then this would have been conflicting with D. Okay. By the way, someone suggested last time that we can solve this problem by moving the definition from the beginning, by moving the definition of D to be after the use of B. Moving D after the use of B would have solved the problem, but compilers don't do this because the compiler doesn't do register allocation and instruction scheduling at the same time. Most production compilers do not do scheduling, moving instructions around and register allocation at the same time because this will be too complex. One of these problems by itself is hard. Each one of them by itself is a hard problem. Scheduling is a hard problem, and register allocation is a hard problem. And most production compilers don't attempt to solve both problems simultaneously. So they schedule the code, and based on the scheduling, they do register allocation, and they don't try to reorder instructions during register allocation.
Yeah, I was the one that actually brought that up last time, but now that brings up another interesting question. Say you end up with a situation like we have where we have a conflict where we have to spill something.
Mm-hmm.
Couldn't it do the reorder at that point and then do reanalyze the live ranges to see if any of the conflicts resolved?
You have to come up with an algorithm that can be implemented. Remember that this has to be an algorithm that can be implemented, that can work efficiently. Yeah. And as you have seen, it's challenging to build a toy compiler for a baby language, right? Building a baby compiler for a toy compiler for a baby language is challenging. Now, solving these problems in a real compiler, in order to do all of this, you'll have to have a complex algorithm that may not be feasible, that may not be implementable. You cannot implement it, and or maybe it's not efficient, or maybe it does not guarantee to terminate. So you have to have an algorithm that is guaranteed to terminate, and it has reasonable asymptotic complexity in order to implement it in a compiler. So remember, keep in mind that compilers, or not only compilers, algorithms in general, software. Software is algorithms. And the algorithm, when it handles a general problem, is not as smart as you when you are handling a small test case manually. So when you are handling this small test case manually, anyone can come up with a perfect solution for this small test case. But the compiler's job is not to solve this small test case manually. Its job is to be able to do register allocation for an arbitrarily big piece of code with an arbitrarily big control flow graph with arbitrarily big basic blocks. So it has to do it in general. And in order to do it in general, you have to have an algorithm that is first guaranteed, that is codable, implementable, that is guaranteed to terminate, and that has reasonable asymptotic complexity. So all of these wishes and dreams that you have may not be realizable. Okay? And that's why there is no compiler that is guaranteed to generate perfect code. That's why the compiler may generate less than perfect code.